Okay, so what I wanted to do with this video is I wanted to go over a little bit of the notation for linear operators and differential operators so that you can actually do your homework a little bit more effectively in both of these topics. They're basically notations, and so once you understand what the notation means, then it gets a lot easier for us to talk about differential equations. Okay, so the first one is our linear operator. And it's going to be represented by L, and oftentimes we're going to have it written as Ly or L of some function f of x. Okay? And it's basically going to give us a definition. So we'll say something like Ly, as an example, Ly equals y double prime minus y prime plus 3y. Okay? And so this is then going to become our definition for this particular differential equation. So what we might see is we might see something that looks like this, L of e to the x. That's going to equal e to the x double prime minus e to the x prime plus 3e to the x, which ends up, because it's just e to the x, is going to be e to the x plus e to the x, or minus e to the x, excuse me, e to the x minus e to the x plus 3e to the x, which is just simply 3e to the x. Pretty simple one because it's e to the x. Let's just imagine that we had, say, something like L of sine x. This would then be sine x double prime minus sine x prime plus 3 sine x, which equals negative sine x minus cosine x plus 3 sine x, which would simply equal 2 sine x minus cosine x. And that's basically all we're going to do with the linear operator, okay? One other way you might actually see it is we might actually get it written as Ly equals, say, 2 sine x whenever we're working with non-homogeneous differential equations. And what this would just basically mean is y double prime minus y prime plus 3y equals 2 sine x. And essentially what that's asking us to do is that would then be asking us to, in fact, go in and solve for y. Solve for the variable in our equation. And that's basically what it's going to be asking for. Okay, and that's how we work with linear operators. Now, the other piece of notation that we have is the differential operator. The differential operator is a stand-in for derivatives, all right, and it allows us to actually picture and imagine derivatives as kinds of polynomials. All right, so there are a couple of things that we need to know about differential operators. One is the basic notation is going to be d, and it's going to have d to some x power. Okay, and that actually implies the x derivative, with, in our case, with respect to x. It could be also with respect to t, it could be with respect to s, it could be with respect to y, right? It all depends upon what derivative that you're actually, what variable that you're actually using. So all we really need to get is that this is the xth derivative. Or you may also see it as the nth derivative. Now, there are two instances where we have to actually understand this particular operator, the differential operator. On the one hand, one is if we have only constant coefficients. So let's take a look at what happens with this differential operator when we have only constant coefficients. So let's say, for example, I have d squared minus 3. Okay, so d squared minus 3, or yep. And so we're going to take this, and let's say it's d squared minus 3y. Okay, now that's going to be the second derivative with respect to y minus 3y. Okay, So basically what we're going to do is we're going to operate, we're going to take the second derivative with respect to y, and then we're going to subtract 3 times that particular function y. And that's basically how the differential operator works. We can choose a different function. Maybe it's not y. We've got d squared minus 3. Say we'll use cosine x. Okay? This will equal the second derivative of x with respect to x, minus 3 cosine x. Okay? So the first derivative of cosine x is going to be negative sine x, and then we'll end up with negative cosine x. So this will be negative cosine x minus 3 cosine x, which equals negative 4 cosine x. All right? So what the d tells me is it tells me take this number of derivative. Okay? Now the neat thing about utilizing constant coefficients is that we can in fact kind of treat these a little bit like they're polynomials. And this actually is kind of a cool thing that we're going to be utilizing a lot when we start to solve homogeneous differential equations with constant coefficients. All right? So let's take, for example, we'll take d squared minus 3d plus 2. Okay? All right? And so we'll have that be our differential operator, and we'll take that by y. Okay. And so now that's going to be y double prime, right? Minus 3y prime plus 2y. Okay, which is great. That's exactly what we wanted. Okay. Now, squared minus 3d plus 2, and we're going to operate it on by x cubed. Okay, so we're actually going to operate on it using an actual function. So now what this is going to end up giving me is it's going to end up giving me the second derivative of x cubed minus 3 times the first derivative of x cubed plus 2 times x cubed. So this is going to end up being 6x minus 9x squared plus 2x cubed. Just take a second to figure that out. Okay. Now, here's a neat thing, though, is that if we have constant coefficients, if the coefficients in front of our differential operators actually happen to be constant, then what we end up having is we end up having something that is, in fact, kind of factorable. Okay? It's a really cool thing. So let's take, and we'll treat d squared minus 3d plus 2 as if it were, in fact, a polynomial. So this is going to end up giving me d minus 2 times d minus 1, x cubed. So what we'll do is we'll first operate on x cubed with d minus 1. All right, we'll do that one first. All right, that's our linear operator. And so this is now going to give me d minus 2 times x cubed prime minus 1 x cubed. Okay? And this is then going to be d minus 2 operating on 3x squared minus x cubed. Now we're going to operate on 3x squared minus x cubed. So that's going to give me the first derivative of 3x squared minus x cubed minus 2 times 3x squared minus x cubed. And that thus is going to give me now, okay, 6x minus 3x squared minus 6x squared plus 2x cubed, which ends up equaling 6x minus 9x squared plus 2x cubed, which is a really cool result. Like, take a look at that, right? Okay. What we did was we factored the differential operators, and what we ended up with was something that essentially was exactly the same. Well, not essentially, it was exactly the same. Which, you know, if you were thinking about these as polynomials, would be, so what? It's a polynomial, but it's not a polynomial. They're actually derivatives, right? And they're higher order derivatives. And somehow, because they were constant coefficients, what ended up happening is that we could actually factor out and end up with the same function after operation. That's kind of cool. It's like something you're like, oh, kind of hard to wrap your head around, but It works. There it is. It's actually really great. A really cool idea, and one that we're going to utilize a lot when we do homogeneous differential equations with constant coefficients. Okay? So that kind of gives us a sense of how to work with things that have constant coefficients. What we have is we can go in and we can either operate utilizing the original equation, or we can factor and do those operations. Now remember, this is like composition. Okay, so d minus 1 we've got to do first, and then we'll do d minus 2 right after that. And then we're going to operate on x cubed. So even though it looks like multiplication, it is not multiplication. Okay, it is operation. We are going to take derivatives. These are differential equations. Okay, now I said that this was different from, say, for example, doing something where we don't actually have constant coefficients. So let's take, for example, let's say we have Ly, okay, equals, and we'll now combine our differential operators. Let's take it, we're going to have d minus sine x. Or actually, we're going to do, d minus sine x. Okay. And we'll multiply that, actually, we'll do that, and we'll take this, will be d minus sine x, and and we're going to operate on, say, for example, we'll do x cubed again. Okay? All right. So now, if I look at this, right, okay, so I've got d, right, so I'm going to take the first derivative with respect to x cubed minus, and this is x cubed sine x. That's it. That's the linear operator. That's how it works, okay? And so this will end up giving me 3x squared minus x cubed sine x. Now let's take a look when I have, we'll call this L1, and I have another one L2, which is equal to d, we'll say d squared minus 3. Okay? Now I have a problem, right? So I take d squared minus 3. So let's take L2, L1, y. And that's going to be just the composition. We'll do L1 first and then L2. So that's going to be d squared minus 3 times d minus sine x. Okay? And that'll be x cubed. All right? Now what's going to happen is that we already know that we're going to end up getting, right? We've got d squared minus 3, and we already know that we're going to get 3x squared minus x cubed sine x. But we have a problem, okay? And the problem is essentially that even though we end up with this, okay, right, since our first operator had this sine x term in it, it changes what our function is, right? Now we've got to take the derivative with respect to sine x, and that actually caused us some problems, okay? And it changes things that it doesn't allow us to basically do that kind of factoring that we were going to be doing before. So this ends up giving me, right, the second derivative, which is going to take a little bit, of 3x squared minus x cubed sine x, okay, minus 3 times 3x squared minus x cubed sine x, okay? And this now, okay, so let me just actually do the first derivative first. So 3x squared minus x cubed sine x prime equals 6x minus 3x squared sine x minus x cubed cosine x. Okay. And then the second derivative, we'll take the derivative of this. It's going to give me minus 6x sine x minus 3x squared cosine x minus 3x squared cosine x plus x cubed sine x, which ends up equaling 6 minus 6x sine x minus 6x squared cosine x plus x cubed sine x. So you can see, like, actually doing these compositions of differential operators can take a minute or two. All right. So wouldn't it be nice if I could just multiply the two of these together, right? Like as if they were polynomials, and then, that'd be my differential operator. Well, it doesn't work that way, right? First things first, I mean, what we'd have here is we'd say, okay, well, so I'll first go with d squared times d, that's d cubed, that's no problem, right? But then I've got to do d squared times sine x. So does that mean I take the second derivative of sine? Or do I call it just sine d squared? I'm not sure. I don't know what that means, right? It's a little bit of a problem, right? And then I have like minus 3d, right? And then minus 3x sine x, all right? Well, notice if that was actually one of the terms that we have a minus or actually a plus 3 sine x, then we should expect a plus 3x cubed sine x. But we don't get that. We actually just get well, we actually are missing something. We need to subtract 3 times 3x squared minus or plus minus 3, excuse me, x cubed sine x. All right, we're not quite done yet. Okay, so this is 6 minus 6x sine x minus 6x squared cosine x plus, and this will then be plus 4x cubed sine x minus 9x squared. Okay? So we do have these terms. It's quite a lot. All right. But still, let's take a look here. I should end up with a 3x cubed or a plus 3x cubed sine x. I actually end up with a 4x cubed sine x. And we have to see whether or not we'd end up with that in terms of our differentiation. So there's all sorts of problems. I mean, like I don't have a way to interpret this. I have all sorts of issues here. So basically, if I'm doing this kind of composition, and one of these terms, like for example sine x, right, is not in fact a constant coefficient, right? 3 is constant coefficient. The number in front of d, constant coefficient. The number in front of d squared, constant coefficient. If one of them happens to not be a constant coefficient, then I can't actually do the multiplication or even the factoring. All right, I'm going to have to, in fact, do exactly what I just did here. I'm going to have to go in, I'm going to have to operate, do this, do L1 first, and then do L2, right? And actually do that composition. All right, so this ends the video. Yeah, so we've got this linear operator, right, which basically just defines for us what it means to it basically just defines for us the differential equation. Makes it a little bit easier to write in case we have to do lots and lots of these, which sometimes we do. We've got this differential operator, right, which tells us what degree of derivative it has, and it'll show up in linear operators, right? We'll define like L as d squared minus 3, for example, right? And then Ly will be d squared minus 3y, right? And so what we have to remember about those is that if we have constant coefficients, we can do the factoring, right? We can factor our differential operator. On the other hand, if I do not have, if like say for example here, this is not a constant coefficient, if that's the case, then I cannot do the factoring. And I'm going to have to go in and actually do each term of the linear operator one by one. Okay? All right. So this completes the lecture.